screen. Also, I guess you guys particularly the attendance form. Also that. So, there you go. Cool. Let me open my video. Come on in. Bless you. You to go away, but you don't want to. All right. Let's get down to business. To defeat the Huns. All right. Every time I say this again, business like this. To defeat the Huns. All right. I was thinking. So, oh yeah, and I'm almost finished writing a practice final for you all. I will post it hopefully today, certainly before next week. When are y'all? When is Lee's final? Thursday. When is Goldsmith's final? Wednesday. When is Alvarado's final? Okay, so yeah, I'll try to get it up ASAP so that you. I mean, so I will say the practice final I'm gonna write is going to be a cumulative one. And clearly the Alvarado final is not going to be cumulative. So you should focus on the parts of the practice final I write that are useful to you, right? Don't practice things you don't need to practice. What else? Actually, yeah, I'll get that posted along with solutions. Yeah, today, tomorrow, something like that. Hearing. Yeah. So that said, I thought we should take a look at. I feel like the Goldsmith practice final is pretty good. I think we can look at that for a bit. If there are certain things you want to ask about, you are certainly welcome to. I don't have a real agenda here. Other than just trying to help you all figure out what you're doing. All right, so let's start with the end. Meaning, let's start with the matrix stuff, and then we'll work backwards to the previous stuff. So looking at this this 20-page thing here, right? I mean, again, right? I said this last time, he gives you a lot of room on each page, right? It's definitely not because it's a super long test. I mean, it's not short, but it's not like ridiculously long. It's just he gave you a lot of space to do your work. But let's start with, yeah, problem, I think 9 on the Goldsmith final is where the matrix stuff starts. Sure. We'll start there. And then again, if there are things you want to see, either from this final specifically or from the Alvarado final, which I also have, you're welcome to just ask. Well, that seems kind of hard to see. Let's zoom in a little bit. I feel like this could be a little bit brighter. Maybe not. I think I might, yeah, I think this document camera is on its, I know I say this like every class now. I think this document camera is on its last legs here. Which is too bad because it's a pretty great little document camera. Let's try closing this and opening it. God. Yes, this clearly needs some help. Now I can't even close this. Sorry. Try again. Okay. Can you guys see that all right? It just seems kind of light, but no, I guess you can see that. Okay. Let's start up here. Find A inverse. Okay, so when you're finding A inverse, you're finding a matrix. So A inverse is going to equal, I would over here find the determinant of A first. So the determinant of A is 1 times 3 minus 2 times 1. Sorry, 2 times -1. That's going to be 3 plus 2, which is 5. So then A inverse is going to equal 1 over 5 times, we're going to switch the 1 and the 3. We're going to change the sign of the off diagonals. Did we do this one last time? I feel like we did this one last time. Maybe it's just they all look the same after a while. And I would leave it like that. No one says you have to multiply that 1/5 through. Don't multiply it through. Don't do more work than you need to do. Certainly you could multiply it through if you need to. It's not terrible. All right, let us look at the next part here. By the way, this next part, right, sometimes problems go together, sometimes they don't. these problems, although it might not look like it exactly, they do go together because really we're trying to solve, bless you, this system. We want to solve the matrix A, 1, 2, negative 1, 3 times the variable vector x, y equal to 3, 2. Oh, look, that is the matrix A from up there. So we know what A inverse is, it's that. So our solution to A times the vector equal to B is going to be the vector equal to A inverse times B, which is going to be our A inverse that we found up there, 1/5 times 3 times negative 2, sorry, not 3 times negative 2, 3 negative 2, 1, 1 times B. This is also a good reason for not multiplying the 1/5 through. We should definitely do the matrix multiplication before we multiply the 1/5 through. That's going to equal 1/5 times, let's see, 3 negative 2 dotted with 3, 2 is going to be 9 plus negative 4. And 1, 1 dotted with 3, 2 is going to give me 3 plus 2. It's very unexciting. It's 1/5 times 5, 5, or 1, 1. And since our answer is so nice, I would go back and check really quick. You plug in 1 for x, 1 for y. Let's see, 1 plus 2 is 3, check. Negative 1 plus 3 is 2, check. Yeah, that checks out. Good. You don't have to check, but if the numbers are really easy to check, you might as well like check it real quick. I should plug my laptop in before it tries to die on me. That'd be a smart thing to do. Okay, I'm just going to keep going. If you have questions, you should speak up. All right. So let us look at the next page, or problem 10. Did you really, you're going to disappear because I plugged in my laptop? Sorry. Yeah, okay. I think it's for real. I think I have to go talk to Sarah and say I need a new document camera. All right, there we go. So let's look at number 10. Find the eigenvalues and eigenvectors of the matrix 4, 8, 1, negative 3. Yeah, I don't love these parentheses. That's fine though. So first we're going to find the eigenvalues. And you're going to do the determinant of A minus lambda I equal to 0. I will point out, because someone was asking me about it today, you could do the determinant of lambda I minus A. If that's the way that you have learned to do it from someone else, that is mother. Wow, it's great. Sorry for the terrible technology here. What's going on? I mean, I know what's going on, but yeah. I know, right? It's like, well, we made it this far. I mean, I guess I can write on the board, but then the people on Zoom can't see what I'm writing. So, okay. Yeah, if it goes out, let me know so that because I'm not really looking at it. So, determinant of A minus lambda equals 0. I will point out it is also technically correct to do the determinant of lambda I minus A equal to 0. But you should do whatever way you've been doing it. So if you don't do it this way unless that's the way you know how to do it. You should do it this way. So we have the determinant of the matrix 4 minus lambda, 8, 1, negative 3 minus lambda. And that's going to equal 4 minus lambda minus 8 times 1. Sorry, 4 minus lambda times negative 3 minus lambda minus 8 times 1. Multiply this out. 4 times negative 3 is negative 12. 4 times negative lambda is negative 4 lambda. Negative lambda times negative 3 is plus 3 lambda. Minus lambda times minus lambda is plus lambda squared. Minus 8 times 1 is minus 8. Rewrite it in the normal way. Lambda squared minus 4 lambda plus 3 lambda is minus lambda. Minus 12 minus 8 is minus 20. Hopefully this will factor. If it does not factor, you can always use the quadratic formula. But it probably is going to factor because if you're having to find the eigenvectors also, it's probably going to factor because finding the eigenvectors when the eigenvalues are not nice integer numbers is not impossible. It's very doable. It's just not pretty. It comes out kind of gross. So on an exam, I couldn't imagine your teacher would give you eigenvalues and eigenvectors where the eigenvalues were this. But that doesn't mean it's impossible. So this factor is lambda minus 5 times lambda plus 4. So we're going to get lambda equal to 5 and lambda equal to 4. Let's find the eigen. Oh, come on, James. What's the real answer here? Thank you. Don't make mistakes like that. Don't try to go quite so fast. All right, so for lambda equal to 5, we're just going to put the 5 back in for lambda in our matrix that's the A minus lambda I. So we're doing 4 minus 5. And actually, I would probably write it out like this on my exam, so that the person looking at my work knows that I know what I'm doing. This times xy should equal 0, 0. You really want to write all of that. And then we have what? 4 minus 5 is -1, 8, and then 1, -8 times xy equals 0, 0. You can use either row dotted with xy. Doesn't really matter which one you pick, unless it's a row of zeros, then that's not going to help you. So occasionally, like when you have things that are diagonal to start off with, if you have a row of zeros, don't pick that row, pick the other row. And so here we're going to get -1 times x plus 8 times y equals 0, or 8y equal to 1 times x. So the vector I'm going to pick is going to be, x is going to be 8, y is going to be 1. Or I guess if I would think about it more logically, I would say if we let y equal 1, then x has to be 8. But really what I'm doing is I'm saying x is the coefficient of y and y is the coefficient of x. That's really how I'm actually imagining it. We'll take the second part. Same deal. 4 minus -4, 8, 1, -3 minus -4 times xy equal to 0, 0. So I've got an 8, 8, 1, 1 times xy equal to 0, 0. And here I would actually choose to use the second row. All right, why do 8x plus 8y equals 0 when you could do 1x plus 1y equals 0? Oh, yeah, question. No, you may not, because that wouldn't be a multiple of this. So I mean, let me make sure I'm in the right spot here. Yeah. So right, if you're trying to find, really you're just trying to find any non-zero solution. So you could also think of this as x equal to 8 times y. So y, I'm going to pick y equal to 1, and then x is going to equal 8 times 1. And the x one should always be the top component, the y one should, or if you're using like u1 and u2 or whatever the letters you have to be, right? They do have this particular place. Whichever way you're writing them here is the way they have to go when you're finding the values for them, or when you're, I should say, when you're picking the values for them. Because we are really making a choice here. I'm choosing y equals 1 and getting x equals 8. You could have chosen y equals 2 and gotten x equals 16, and that would also be perfectly valid. All right. Here I would use the second row equation, 1 times x plus 1 times y equals 0 to get y equal to -x. So if I pick x equal to 1, then I'm going to get y equal to, right. And I might label, one sec. I might label this as lambda 1 and this is v1. This is lambda 2 and this is v2, just to kind of distinguish them from each other. Yes. Yes, with rare exception. And I'll give you an example of that in just a second. But yeah, you could have also used 8x plus 8y equal to 0 and gotten the same eigenvector. The only time when you can't pick either row is when you have something like this. So let me grab a piece of paper here. Other blank paper. Gosh, do I have? Yeah, I have paper somewhere. So if, for example, typically, I know it almost always happens when your matrix is upper or lower triangular or diagonal. So if your matrix was something like, I don't know, 4, -7, let's say we had a 2 up here and a 0 down there. I would probably still recommend showing the work, but every single one of you should be able to tell me without writing anything down what the eigenvalues of B are. Oh, yeah, I mean, if you could see it, sure. Everyone should be able to tell me that the eigenvalues of B are, what's the positive one? And what's the negative one? Right? Because when you have a 0 there or there, your eigenvalues are always going to be the diagonal elements. Now let's show the work just so that we can see what's happening, because it is nice to remind ourselves of why. We do the determinant of B minus lambda I. That's going to be the determinant of 4 minus lambda, 2, 0, -7 minus lambda. And that's going to be 4 minus lambda times -7 minus lambda minus 2 times 0 equal to 0. Do not multiply this out. If this is 0, you've already got it factored for you. You have 4 minus lambda times -7 minus lambda equal to 0, which means either lambda is going to be 4 or lambda is going to be -7. Do not multiply it out if you have a 0 right there. You're wasting time. Okay. So then to answer the question about can you pick either row, and I don't remember, we'll just do both eigenvalues here just to see it. So if we have lambda 1 equal to 4, then our matrix is going to be, see, 4 minus lambda is 0. This is not the one I want. That's all right. 2, 0, and -7 minus 4 is -11 times x, y equal to 0, 0. This is still worth seeing because this one I think is a little bit confusing for people sometimes. So first row, first column, 0 times x plus 2 times y equals 0. This is one of the times when you don't get to pick anything. Well, that's not true. You don't get to pick everything. So when I solve this, 0 times x goes away. I'm just left with 2 times y equals 0. If I divide both sides by 2, I get y equals 0. We didn't pick that. We just end up with it. And if y equals 0, what am I going to choose for x? Right. You can choose anything you want that's not 0, but we almost always choose 1. You can even check, right? If you multiply this matrix by 1, 0, you're going to get back. Interesting. Yeah, 0, 0. Yeah, which you should. Okay. Let's look at lambda 1 equal lambda 2 equal to -7. So if I do that one, then plugging that in here, I get 4 minus -7, which is 11, 2. And then the second row is going to be 0 minus 0. Oh, sorry, not 0 minus 0. 0 and then -7 minus -7, which is 0. And what I wanted to say is that you can't use the second row here. It's not going to help you at all. The second row just says 0 times x plus 0 times y equals 0, which is true, but doesn't tell you anything about what x and y have to be. So in this instance, you have to use the first row because that'll give you 11x plus 2y equals 0, or 2y equals -11x. So everybody should take a minute here to write down the eigenvector, preferably using not fractions, also known as integers. All right, that was enough time. I'm going to get x equal to 2 and y equal to -11. That is the easiest choice. X is the coefficient of y is the coefficient of x. That will always work. There's no more to say. That will always work. Right? If I plug in 2 for x and -11 for y, -11 times 2 is -22, and -11 times 2 is -22. So it definitely solves that equation. Cool. All right. I'm going to keep going if you don't stop me, which is fine. Like, it's just a reminder, you can ask questions. Yes. Right. If you end up getting one of the two parts of the eigenvector equal to 0, the other part has to be any non-zero number you would like. And the number that we all usually like is 1. But any other choice is a valid choice. You're welcome. All right, let us look at, then these long questions. Okay, so, okay. Sure, we'll skip I'm skipping the matrix thing, the not matrix thing for a moment, just so we can focus on those. Sure. What's that? Oh yeah, I just want to say, I think there's one other thing which I think we'll skip. Yeah, so there is on the Goldsmith final, there is one of those. Right, the PAP inverse stuff, which I think we've done enough of that we shouldn't spend 30 minutes doing that. But you should be prepared, right? You're gonna have to do, I mean, I can't imagine you're not gonna have to do a problem like this. I could be wrong and we all rejoice, but I'm probably not wrong. It's probably right. He's asked you like 4 homework problems on it and it's on the practice final. It's a pretty good bet it's going to be on your actual final. Yeah, so okay. Good enough. Let's go back and look at some of these integrals. I guess, I mean, for an Alvarado's class, I guess you could leave if you wanted to. But I mean, I would stick around personally, but you don't have to stay. You never have to do anything, right? Okay. Right. I thought you have to pay taxes. Or no, you don't. You can go to jail, right? There's always I had a homeroom teacher like when I was in 7th grade who was like, you always have a choice. The choices come with consequences. So you can always choose to do whatever, except die, right? That's the only thing you don't have a choice about. Everything else is a choice. There are just consequences involved with the choices you make. So not that I'm saying there's consequences for leaving class. If you wanted to leave class right now, you're totally well. There's no consequence other than you won't get a piece of candy because I'm going to give you all candy in the class. So I guess it's a consequence. All right. Oh, that's the other thing I want to say is if you haven't already, please do fill out the course evaluation. I know I've like written about it a couple times in announcements. So if you haven't done that already, at the top of the modules in Canvas, there's a link to a course evaluation. It doesn't take that long to fill out. It's just a few questions. They're anonymous. I don't know which of you writes whatever. I just get to see like the aggregate results of things you've written. Usually it's a nice thing usually there are nice things written, but if you have a critique, that's also perfectly fine. I do take that feedback and read it and try to implement it in future courses I teach, but we'll see. We'll see how I do. All right. This first problem, I think pretty straightforward. Trying to find the exact value of the definite integral. Let's talk about how much work we should show. So first, we're going to anti-differentiate this. We're going to get x squared. We're going to get what? X cubed over 3 minus 3x squared over 2 plus James, I don't know about that, 2 times the antiderivative sign of pi x is it positive or negative cosine? The derivative is positive cosine. The antiderivative is negative cosine. So we're going to get negative cosine of pi times x divided by pi, the coefficient of x, evaluated between 0 and 2. Oh, yes, of course. Yeah, sorry, it looks perfectly, well, we'll see. Yeah, you might be asking for a lot here. Jinxed myself. I shouldn't have said anything. Oh my God. Yeah. Oh, I have to turn it off and turn it on. Sorry. I don't blame you. I blame me. I mean, I blame the device really. Okay. Cool. There we go. Zoomed in. Yeah, zoomed in. So if it were me on an exam, I would do this. I would say, great, plug in 2. I'm going to get 8/3 minus 3 times 4 is 12 over 2 plus 2 times, okay, negative cosine of 2 pi. I would probably just write negative cosine of 2 pi. Even though I know what that is. All over pi. Minus, I'm plugging 0, I'm going to get 0 minus 0 plus 2 times negative cosine of 0 over pi. And I would stop there. Leave it like that, even though I feel terrible about leaving it like that. I hate myself for leaving it. Nah, I don't like that I've left it like that. But if you are, right, this is a long test. You got other things to do. Simplifying this to the next iteration of this is not probably worth that many points. So I would stop there on an exam. But then if you wanted to, then do all the work you can. And if you have time, come back and simplify it. So we simplify this. Okay, sure. 8/3 minus 6. Cosine of 2 pi is 1. So that's a negative 1 times 2. So that's a minus 2 over pi minus, and then cosine of 0 is also 1. So that's going to be a minus, so that's going to be a plus 2 over pi. And oh, look, those 2 over pi's cancel out. You end up with 8/3 minus 6, which is some negative number, which is totally fine. It is negative. That's okay. I probably wouldn't simplify that though. Yeah.
Would it put plus C?
No, I would not. Why wouldn't I put plus C? Because it's definite. Definite integrals, when you have limits of integration, there's never a plus C. Or there is a plus C, but the plus C here and the plus C here cancel each other out. All right. So the next one. This one we're going to rewrite as the integral from 1 to 3 of 1/2 times x to the negative first minus x to the negative 2 plus 2x to the negative third. I might not actually rewrite that first part there, but I did. So then integrating, the constants hang out in front. So I'm going to get 1/2 times, what's the antiderivative of x to the negative 1? Or 1 over x. Right. It's easy when you think it was 1 over x. It's impossible if you're like x, what's x, right? So it's going to be the natural log of the absolute value of x minus x to the negative 1 over negative 1 plus 2 times x to the negative 2 over negative 2 from 1 to 3. For me, I would probably simplify this expression before plugging in just because these don't look like what I like. I would write this as 1/2 natural log of the absolute value of x minus a minus is plus x to the negative 1 is 1 over x. 2 divided by negative 2 is negative 1. So it's minus x to the negative second is 1 over x squared. 1 to 3. And then I would plug in and I would get 1/2 natural log of 3 plus 1 over 3 minus 1 over 9 minus 1/2 natural log of 1. Notice I didn't write absolute value. I didn't write absolute value because the absolute value of 3 is 3 and the absolute value of 1 is 1. So you don't need to write it if you're taking it. Plus 1 over 1 minus 1 over 1. Again, if I'm strapped for time, especially at the beginning of a test, I'm stopped for time. Right? I'm always stopped for time on the first page. I'm stopping there, I'm moving. But then if I come back, I can see that the natural log of 1 is 0. 1 minus 1 cancels. And I'm left with 1/2 natural log of 3 plus 1/3 minus 1/9. That's good enough for me. Sure, you could say that's 3/9 minus 1/9 to make it 2/9, but okay, fine. 1/2 natural log of 3 plus 3/9 minus 1/9 is 2/9. But that's about as good as it gets. But again, I'm going to try to emphasize as much as I can. Don't spend too much time trying to make things look pretty. I mean, don't like write as nicely as you can, but spend your time doing the calculus part of this and less time doing the addition, subtraction, multiplication. That is not the important part. It is still, it's not important, but it's not the meat of your sandwich of a test. It's like the mayonnaise or the mustard. Mustard, preferably, but you know, whatever. All right, this is kind. I would never give you this. Giving you the u substitution. All right, so we're going to let u equal 2 plus x cubed. Du is going to be the derivative of this times dx. You can do this whatever way you like. I personally like to say, oh, look, I have x squared times dx. So I'm going to make this look like x squared times dx on the right-hand side. So I'm going to multiply both sides by 1/3. Say that 1/3 times du is equal to x squared times dx. So when I rewrite my integral, the integral of, I'm going to rewrite this actually as 1 over the square root of 2 plus x cubed times x squared times dx. And then I'm going to say, okay, x squared times dx is 1/3 times du. And 2 plus x cubed is u. So when I translate this to the language of u, equal to the integral of 1 over the square root of u times 1/3 du. You have to make sure all of the x things have become u things before you can try to do the antiderivative. Especially making sure that the dx part transforms into the du part. All right, and then we should definitely rewrite this. Let's write it as 1/3 outside of the integral times u to the negative 1/2 du. Sorry, I forgot the word integral. 1/3 times the integral of u to the negative 1/2 du. That symbol there means we need to find the antiderivative. So we're going to anti-differentiate. We're going to get 1/3 times u to the positive 1/2 divided by 1/2 plus c, right? This is going to get a plus c because it's an indefinite integral. There are no limits of integration up here. And then we're going to simplify. Dividing by 1/2 is like multiplying by 2. So we're going to get 2/3. I wouldn't, well, no, I wouldn't. And then we do have to replace u with what it's equal to in terms of x. So u was 2 plus x cubed. And the reason you have to do that is because if you start off with an integral of a function with x's in it, your answer has to be a function with x's in it if it's an indefinite integral. You have to end with the same variable you started with. Do this for your teachers. It's good for you too, right? Like box that answer, circle that answer, whatever you like to do. Make it clear where your answer is so they can be like, yeah, there's their answer. It looks right. Or there's your answer. It doesn't look quite right. Let me go look at the work they did to see where they went wrong and where I'm going to deduct some points. But it's good for you, I think, to box your answer like that. Ooh, integration. So again, I guess in Goldsmith's class, you can maybe expect to get nice instructions like this where they tell you what method to use. I wouldn't expect that in either of the other classes, unless your teacher is specifically written, well, you know, in Lee's class, there isn't a practice exam, but in Alvarado's class, I don't think there's any instructions about like, well, there's no integration, so okay. All right, so integration by parts. So we have to pick what's going to be u and what's going to be dv. So should u be the 2 theta plus 3 or the cosine of theta over 2? Wow. Do I have a log? Definitely not. Do I have a power of my variable? I sure do. 2 theta plus 3 is the thing that's a power of theta. It's 2 theta to the first. Really, when you say this should be like any polynomial. That's even too specific. It's just anything that's like your variable raised to powers. 1, -1, right? It could be anything, but this is definitely our choice for you. And the rest gets to be dv. So here's how I would tackle this definite integral with integration by parts. Let's do it indefinitely first. So we're going to do the integral of 2 theta plus 3 times cosine of theta over 2 d theta. My u is going to equal 2 theta plus 3. My dv is the rest, cosine of theta over 2 d theta. Then what's du, everybody? What's the derivative of 2? I know the theta is confusing, right? It shouldn't be, but it makes it look just harder. Pretend theta is x. Right, the derivative of 2x is 2 d theta. You should still write theta if there's a theta there, even though you're calling it x in your head. Call it x in your head, write theta on your paper. And then v is the antiderivative of cosine of theta over 2, so it's going to be positive sine of theta over 2 divided by what? Divided by. Not we'll flip and multiply it, but it's divided by what? Divided by the coefficient of your variable. Just like when we were doing the integral of cosine of pi x, we got negative sine of pi x divided by pi, the coefficient of the variable. Okay, and then I would definitely write that as 2 times sine of theta over 2. All right, so then this is going to equal u times v. So 2 theta plus 3, we definitely should throw some parentheses around that, times 2 times sine of theta over 2 minus the integral of v du. So 2 times sine of theta over 2 times another 2 d theta. And then we still have to do one more integration, right? The whole point of this process is we didn't finish it, we just made the integration easier. But now we still have to do the integration. So it's going to equal 2 theta plus 3 times, I guess I could have distributed the 2 there, whatever, I didn't. And then minus 4 times the antiderivatives, I should have adjusted, oh, I can adjust. What's the antiderivative sine of theta over 2?
2.
Right, so let's make it a plus 2 cosine of theta over 2. Let's double check. The derivative of cosine would be negative sine. Oh yeah, we're good to go. Okay. So then finally, after all that, then I would go back and say, okay, there's my antiderivative. I don't need a plus c because it's just my own work for my own self. So then I'm going to go back and say, okay, the integral from 0 to pi of 2 theta plus 3 times cosine of theta over 2 d theta is equal to exactly that. And I guess I could simplify it a little bit. 2 theta plus 3 times 2 times sine of theta over 2 plus 8 times cosine of theta over 2 evaluated from 0 to pi. That is how I definitely recommend ever doing a definite integral where you have to do integration by parts. Yeah.
Is it bad? Because so what I did is I definitely integrated the first part first, like the 2x plus 3 times 2 sine x over 2 first.
Okay.
And then I definitely integrated the second part after, and then like added it together.
That's fine. That's not how I would choose to do it, but it's
Yeah.
totally fine to do that. And but yeah, so you evaluated when you plugged it. Yeah, totally fine. So then plugging in pi, I'm going to get 2 times pi plus 3 times 2 times sine of pi over 2. What's sine of pi over 2? 1 plus 8 times cosine of pi over 2, which is 0, minus 2 times 0 plus 3 is 3 times 2 times sine of 0 is 0 plus 8 times cosine of 0, and cosine of 0 is 1. So this definitely is meant to be not terrible to simplify. So we simplify this, we've got 2 pi plus 3 times 2 times 1 plus 0 minus 8 times 1. So this simplifies actually as 4 pi plus 6 minus 8, which is just 4 pi minus 2. Again, right, even though that's right, if I was strapped for time, I'd probably stop right here and not even worry about figuring out what cosine of pi over 2 is or sine of 0 was until I had done the rest of the test. Okay. Ooh, partial fractions. Everyone's favorite. Let's talk about how to set this up. Yeah, interesting the way they phrase this here. So, so if they tell you you have to use partial fractions, that means we should be able to do what to the denominator? Factor it. I can factor out an x. So 2x cubed plus 5x squared plus 2x. Definitely, I can factor out an x. I'm off to 2x squared plus 5x plus 2. And I'm betting this factor, well, it has to factor because we don't know how to do the other part. So this should factor as 2x and an x. And then I have to be able to multiply the 2. And it has to be positive, so it's got to be a positive 2 and a positive 1. So there's not a lot of choices here. So it's either a 2 here and a 1 here, or a 1 here and a 2 here. And I think it's got to be a 1 here and a 2 here. So the 2 times 2x plus 1 times x gives you 4x plus x, which is 5x. Cool, that's not so terrible. So then we're going to rewrite x plus 1 over x times 2x plus 1 times x plus 2 as a over x plus b over 2x plus 1 plus c over x plus 2. Okay. Then this is the step I feel like people kind of forget about. Then you're just gonna multiply both sides by the common denominator. So multiply everything by x times 2x plus 1 times x plus 2. The left side, you should always get just whatever your numerator is. The right side, a over x times this, the x's cancel. You get a times 2x plus 1 times x plus 2. B times the 2x plus 1's cancel, and you get b times x plus 2. And c, the x plus 2's cancel, and you get c times x times 2x plus 1. There's no good reason to put parentheses around that x there. I just happened to write them there. And then, especially if there aren't any repeated linear factors, right? You don't have any of these things raised to a higher power. Pick your nice values of x. Pick your convenient values of x. What's one of my nice values of x? Definitely. What's another one? What's the last one? Almost. -1/2. Right? We're just picking the values of x that make either that factor or that factor or that factor 0. So you could literally find them by setting x equal to 0, 2x plus 1 equal to 0, and x plus 2 equal to 0, and get x equal to -2, x equal to 0, and x equal to -1/2. But that is really the easiest way to do this. I cannot say it is. There's no better way to do this. So then plugging in -2 for x, you have to plug it into both sides. You get -2 plus 1 on the left equals a times 0 plus b times 0 plus c times -2 times -4 plus 1. So I have -1 equal to 6 times c, so c equals -1/6. Same deal for x equal to 0. If I plug in 0 for x, I get 0 plus 1 on the left equal to a times 1 plus, a times 1 times 2 plus b times 0 plus c times 0. So I end up with 2a equal to 1, which gives me a equal to 1/2. And finally, plugging in -1/2 is going to be a little bit more work, but not a lot. -1/2 plus 1 equals a times 0, because that part's going to be 0. Which one should not be 0? The one with the a, the b, or the c? The one with the b, right? Because I've already found the one, the c and the a value. So I should be getting 0 here, and then b times -1/2 times -1/2 plus 2, which is positive 3/2, and then c times 0 as well. So then that's a little bit gross. I've got 1/2 equal to b times -3/4. Multiplying both sides by -4/3. I get -2/3 equals b. Okay. And then I ran out of room. But then the last part is you have to go back and integrate the thing, right? You're trying to find the antiderivative. So the antiderivative of x plus 1 over x times 2x plus 1 times x plus 2 is equal to the antiderivative of a over x, and a was 1/2, plus b over x 2x plus 1, and b was -2/3 over 2x plus 1, and c over x plus 2, and c, oh, you're welcome to a candy bar. There's some stickers and some M&Ms. They're from Halloween, but they're perfect. My wife was like, we're doing full-size candy bars this year, so yeah. She was very excited, and so were the kids, but there were some extras, so thought you guys would like them. And then the last one here was c, which was -1/6 over x plus 2. And then we actually have to do the integration, right? So we're going to get 1/2 natural log of the absolute value of x minus 2/3 natural log of the absolute value of 2x plus 1 divided by what? I'm going to say times 1/2. And then finally, -1/6 times the natural log of the absolute value of x plus 2. Plus c. Yeah.
When is it like when we do the a over whatever, it's like a x plus b.
We don't do that in this class.
Oh.
I don't think we were taught, that's a thing you do when you have an irreducible quadratic factor, like if you have something over like x squared plus one. I don't think we ever talked about that. I'm pretty sure it's not usually covered in this class. So yeah, but that's when you would do it. If one of your factors was like x squared plus one, which can't be factored further. Yeah. All right, yeah. Did I write it? I wrote it as I guess it looked like a 2 to me. So I wrote it as a 1/2. That should be that's a 6. Can't you tell? There, yeah, that's what happened to it. It's I wrote it wrong. Let's see. So we've got just a few minutes left here. Let me scan through this and see if there's anything that seems really pertinent. Ooh, let's do that. Let's find the solution to this inhomogeneous ordinary differential equation. So looking at this, it's certainly written in a way that it looks like we should probably just use first order linear stuff. So I'm going to find my P of t is 1 over t plus 1. My mu is e to the integral of P of t, which is going to be e to the natural log of t plus 1. And we definitely should simplify this as just t plus 1. I'm pretty sure we got to show our work here. So multiply everything by t plus 1. So you're going to have t plus 1 times y prime plus t plus 1 times 1 over t plus 1 is 1 times y equal to t times t plus 1. The left-hand side is always a product rule. This is always going to be the derivative of the product of whatever is multiplied by y prime. In other words, mu times y. This here, I'm just going to say this again. That here is always going to be the derivative of the product of your mu and your y. Every time. Every time. Every time. Equals t squared plus t. Right, distributing that out. And then we're going to anti-differentiate both sides. We're going to say that t plus 1 times y is equal to the antiderivative of t squared plus t. And then we're going to say that y is equal to, we're going to divide both sides by t plus 1. We might as well do the antiderivatives because we know how to do it. That's going to be t cubed over 3 plus t squared over 2 plus c. I wouldn't distribute this. Oh, actually, not true. I probably would actually distribute it because I like to, but I don't think we should distribute it normally. But then we do have to use the initial condition to solve for c. So we're also told that y of 0 is equal to 1. So plug in 1 for y and 0 for t. And let's say we're going to get c equal to 1, right? 1 times c equals 1, so c equals 1. And then you're technically not done yet. You have to go back and rewrite your solution as y equals 1 over t plus 1 times t cubed over 3 plus t squared over 2 plus 1. Another solution. All right. That's all we got for today. It's been great. Enjoyed seeing you all. Taking 17C next quarter. There's a co-class. Sign up for it. Come see me. We'll do the same thing again. It'll be lots of fun. If you're not, I'll miss you. And come get help next week if you need help next week. What time, for those of you who have your final on Monday, what time is that on Monday? Okay, so you got time on Monday, like to review things, to prepare for your final. But yeah, and I'll try and get that practice final up today and solutions up tomorrow. Yeah. Yeah, so next week, all myself, Grant, Sarah, Jen, we will all be findable in Drop It. That's the only place we'll be. We will not be in C class. We will not be in CADS. We will just be in Drop It. At the library. But when we say Drop In, we mean Shields Library, the basement of Shields Library. The lower level, so it's technically was the basement. Okay. And take a piece of candy. There should be enough for everybody to have one piece. There's Snickers, there's M&Ms, there might be a Milky Way in there.
Thank you so much.
You're very welcome. There's not enough. I've got an extra piece or two in my bag here. You're very welcome.
questions
Yes, you may, Maggie.
Projections.
About what?
Projections.
Sure, yeah. Oh, yeah, we should know one of those.
I forgot how to do projections.
I do have a couple extra pieces if there's not enough in there, really. I got Snickers right here. Just one, yeah, sorry, there might not be enough, I'm sorry. Is there not enough?
That's okay.
No, I feel bad. If you come to me next, no, yeah, I'm so close to having enough for them. Sorry.
Thank you. No,
I do have one more candy bar in my office if you want.
it's okay.
Okay, yeah, let me stop the video for a second here.
No, I forgot how to do them because I'm like,
Oh,
it's like, oh, you guys should just know your vectors and matrices and a bit of integrating factors. And I'm like, okay, matrices, easy. Eigenvalues, sure. I forgot how to deal with
Projections,
projections and vectors.
so the projection is,
Cosine theta.
well, right, so basically,
And like,
I'm sorry,
they're like, oh, it's a shadow and projected.
Right.
I'm like, what is that?
so you can just